In the last section of Chapter 7, we deal with Bayes' theorem, which is working more with conditional probability. And there's a pretty complicated formula that goes along with it, although there is some way of patterning it to make sure you have all the components. But mostly what I'm going to show in this, although I will show how to make use of the formula in one instance, I'm going to show that under a lot of circumstances, if you either make a Venn diagram or a table, they sometimes say make a tree diagram, but that still requires you to have to go backwards and use some logic and actually use Bayes' theorem's formula to actually complete it correctly. Whereas the other methods, you can kind of complete parts just by knowing, what's missing, and doing some simple additions and subtractions and things like that. But so I'm going to show you some ways of doing situations where Bayes' theorem is needed with diagrams as well. And basically, what this comes out from is if you have enough information and you're given the probability of A given B. Sometimes what's going to happen, once you have sufficient information, is you have to say, okay, well, if I want the probability that A occurs given that B has occurred, what's the probability that B occurred given that I know that A occurred? Now, if they're independent events, that doesn't matter. They're both the same because, the given that part doesn't matter. But if they're dependent events, you're not going to find many situations where the probability of A given B and the probability of B given A are going to be equal to each other. So a lot of students think that they might be complements of each other, but that's not the case either. That's not necessarily true. So Bayes' theorem becomes necessary because if you have one of the conditional probabilities, the other one is not always necessarily easily found unless you organize your information a certain way or you use the formula that Bayes' theorem actually is associated with. So to get into it, typically if you have a situation where Bayes' theorem has been utilized in some way, if you had a Venn diagram of it, you would have something that looks a lot like this. Because basically what's going on here is you have three mutually exclusive events that could occur in an experiment. So that would be like one characteristic of, whatever data I'm collecting or the subjects of the experiment that I'm examining, whatever the case may be. And then there is this third thing that could occur in any one of them. So basically I have these three groups which, one of the given subject of the experiment is going to fall into, but there's another subgroup, that either they're going to have this other characteristic or they're not going to have this other characteristic, but that characteristic can occur across all three groups or even more. So what you see here is an experiment in which three mutually exclusive events, A, B, and C, form a partition of the uniform sample space depicted in the diagram. Draw a tree diagram using the information given in the Venn diagram illustrating the probabilities of the events A, B, C, and D, and then you're to answer the questions over there given that information. Tell you with all honesty, you really don't need the tree diagram. They kind of use a tree diagram to kind of show you how Bayes' theorem's formula comes about. But generally, what I can look and see here, first of all, if I add up all those numbers, it is 100. So these are basically percentages, but they're also being represented as numbers. And one of the things you want to make sure you're aware of is since oftentimes Bayes' theorem is starting with information that deals with percentages or proportions of another proportion that's already been done. You have to take that in consideration and realize that if you try to make use of it and to put it into a Venn diagram or a table that makes more sense, you may start getting information that you might think at face value that can't make sense. Like if I'm talking about number of people and I get like 36.36 or something, well, I can't have 0.36 of a person. I have no idea what that means. But if you're dealing with percentages, you don't necessarily know, especially if they don't tell you, how many people were in the experiment to begin with. So, with that being said, and you can assume, that these are dealing with primarily percentages, and because they're dealing with percentages, if you try to think of them in whole number syntax, that you're not going to lose any, possibilities because of the fact that you're getting decimals when you expect not to have portions of whatever it is you're examining. But when I look at this, I can see that I have 35 people in Group A, 35 people in Group B, and 30 people in Group C. The only thing that's really different is that some of them are in Group D as well, and some of them are not. So when I draw my tree diagram, the first split I see is A, B, and C. You notice I am putting the probabilities down. And that's 0.35, 0.35, and 0.3, because that's 35%, 35%, and 30% for me to be going to each one of these groups. Now, once I'm in each one of these groups, so right now I have basically 35, percent of the overall populations in Group A. Well, 20 out of that 35 is in Group D as well. So 4/7 of that is in Group D, 3/7 is not. Same thing with B. B, I have now 25 in Group D, 10 that are not, so that's 5/7 to 2/7. And for C, I have 10 out of the 30, so it's 1/3 and 2/3 for D and the complement of D, respectively. So, respectively. I always say respectfully. So, when they ask you, the question, what's the probability of D? And if I had a tree diagram, I'd have to do the probability of D given that C occurred, which is 1/3, the probability of D given that B's occurred, the probability of D given that A's occurred, and add all those together. Which is what I would basically be doing if I was looking at the diagram. I could see, well, what's the probability of something being in D? Well, I can see that 20 plus 25 plus 10, or 55, is in D, and that I have 100 in total. So basically, if I look at the diagram, I could just add those numbers that are in D and take it out of the total number that's in this entire set, and I would get 0.55. If I was using a tree diagram, which is how they come up with the formula for it, I would have the probability of D equaling the probability of D given A plus the probability of D given B plus the probability of D given C. And basically, I would have to do 4/7 of 0.35, 5/7 of 0.35, and 1/3 of 0.3. Add those together, and I would get the 0.55. It's just, if you can find a way to get that diagram, then everything would be, much more easily done because you could see it. It's a much more clear visual. But sometimes, depending on the information that you may have in front of you, you may have to calculate some things first before you can actually put together that diagram accurately. But the rest of these questions become pretty easy, especially if I use the Venn diagram I was given. The probability of A given that D has occurred. Well, again, I have 55 in Group D. I have 20 of them that are in Group A. So if I know that they have to be in Group D, I'm only looking at that 55, so 20 out of the 55 would be in Group A, and so I would get 0.36 repeating. Find the probability of the complement of D. Well, if I had the diagram in front of me, I could easily just say, okay, well, it looks like I have 25 and 20 out of 100, or 45 out of 100, 0.45. Or I could also realize that by the rule of complements, the probability of the complement of D should be 1 minus the probability of D. And 1 minus 0.55 is also 0.45. So you have a couple of options at that point. The probability of B, given that you're not in Group D. So if I'm not in Group D, I can see again I have 45. So I'm looking at that 45. 10 out of that 45 are in Group B. So 10 out of 45 becomes 2/9, which is 0.2 repeating. But as I said, sometimes they don't give you the diagram, and what if you have information here, and you're looking for the probability of A sub I given that E has occurred, where A 1, 2, 3, all the way through n is a partition of a sample space. So these are going to be mutually exclusive groupings in a sample space, with E an event that can occur across all of these other partitions, all these other sub-events of sample space S. If I want to do the probability of A, any one of those A's given E, what I would have to do is first figure out what the probability of A in general is, times the probability of E given A, which is often something that's a little easier done. And then I would have to take each one of those sub-probabilities, probability of A1 times the probability of E given A1, plus the probability of A2, times the probability of E given that A2 has occurred. One of those probabilities are going to be the same as what you have on top there. So whatever I represents, if it's like the third split, the fourth split, it's going to be both in the top and bottom as part of an addition problem. So for instance, how will we make use of that? If a certain disease is present, then a blood test will reveal it 95% of the time. But the test will also indicate the presence of the disease 2% of the time when in fact the person is free of disease. If 0.3% of the general population actually has the disease, what is the probability that a person chosen at random from the population has the disease, given that he or she tested positive? So in this particular problem, before I get you started on this, let's kind of wrap some things up here. I'm going to let the plus sign mean that I tested positive, and I'm going to let D stand for having the disease. So what we're looking for here is the probability of D given that I have a disease, given that I did test positive. If you look at the information that you're given, I just want to show you really quick. The information that we're given is that, okay, well, the green one, if the disease is present. So I'm given that the disease is present. I have the disease. Of getting a positive blood test is 0.95. So that's the probability of positive given that I'm diseased. Notice it's not the same thing as the probability of me having the disease given that I tested positive. I want to know, what that probability is, because that's important to me. Because if I took a test and it tested positive for the disease, I want to know what the likelihood is that I actually do have it. In blue, we're given that the probability of being positive given that I don't have the disease is 2%. And of course, the probability of me having the disease is 0.003. So that's the information that we have. So based off of that, and based off of me clarifying some of this information in here, which ultimately you're going to be required to do, I want you to figure out what the probability of having the disease given that I tested positive. I want you to figure out what that probability is. So take a moment, compute that, and then we'll go back over it. Okay, so now if you do this the correct way, you could probably, because you could probably, use a diagram to do this. The one thing that you may have some difficulty with, although it doesn't seem to be a huge issue with this, is, you would have to be careful about how you define your subgroupings. Because, the test would be the subgroupings. So apparently you're able to have the disease if you test positive or not. Well, your results could be, positive and negative, or you could even say, well, there's positive, negative, and inconclusive, and you really don't know how those other two groups are forming. The best thing you could possibly say if you're going to use a diagram is that you're going to have positive and not positive for your two mutually exclusive events, because I can't test positive and not positive. I could test, still mutually exclusive, but doesn't, it takes both into consideration that I could have a negative or an inconclusive test as well. But for the sake of argument, I'm going to show how to make use of Bayes' theorem's formula to do this. In the rest of my examples, I will kind of use either a Venn diagram that I've come up with or a reestablished table that I've come up with as well. But for this one, I'm just going to use the formula. So, according to Bayes' theorem's formula, well, there's some information I'm going to need to know. So I'm going to find some additional information that's pretty easy to have based on the numbers I already got. If the probability of me testing positive, given that I have the disease, is 0.95, then the probability of me not testing positive, given I have the disease, is 0.05. That stands to reason. The probability of me testing positive, given I don't have the disease, is 0.02, which means the probability of me not testing positive, if I don't have the disease, is 0.98. And then, of course, the probability of, since the probability of me having the disease is 0.003, the probability of me not having the disease is 0.997. Because some of these are going to be needed as I go through Bayes' theorem. Because if I'm going to do the probability of D given plus, then I'm going to do the probability of D times the probability of positive given D, which I was given, which I had, over, well, that product again, the probability of D times the probability of positive given D, plus the probability of not D times the probability of positive given not D. So I had to figure out these things more so, and what's most importantly, because I needed this probability right here. Without that, no, sorry, not that one. But they gave us all the probabilities, actually. Just want to make sure I had them all. Well, no, I needed this probability down here. That's the one. I circled the wrong one. That's why. I needed that probability. I needed to figure out that probability in particular in order for me to be able to come up with the calculations I needed. Depending on what other kind of options there are, you may have several options down there, as what's indicated in the formula. So if I substitute these values in now, on top I have 0.003 times 0.95. On the bottom I have 0.003 times 0.95 plus 0.997 times 0.02. And when that's all said and done, and I calculate it, I get about 0.1251. So the probability of me actually having this disease, given that I tested positive, is about 12.5%. So, that could be a sigh. That could be a sigh of relief, or that means that you may have to go through more testing, before you get over concerned about it. Now, be careful with this one, because I'm going to point out something again really quick. Notice here it says, okay, a poll was conducted amongst 500 registered voters in a certain area regarding their position on a national lottery to raise revenue for the government. The results of the poll are shown in the accompanying table. So what you see there is you have percentage of voters polled. These are all percentages. The thing you have to be careful of is sometimes students want to treat percentages as numbers all the time. You can't do that. Because, for instance, if I try to do that, that's telling me that, favoring the lottery, the people who are surveyed, 130% of them favored the lottery. Well, that can't happen. It's impossible. I can't have more people favoring the lottery, especially when I see people don't favor the lottery, than the people who I actually looked at. So take a moment, figure out the probabilities of this, and then we'll go over it. Okay, so with this, we have to actually use the numbers, or I have to be more careful with the percentages, because those percentages I focused my attention on before I gave you a chance to work on this, are dealing with the percentages of males. So 62% of males who were polled favor the lottery system, 32% of the males don't, and 6% have no opinion. So if you're not careful about how you treat these as numbers, it can sometimes cause issue with your accuracy of your results. So what I'm going to do for this to make my life a little easier is I'm going to construct a table here where I split it between male and female, but I also have these groups: favor, do not favor, or no opinion. I could try to set up a diagram or a Venn diagram for this, but I wouldn't have just one region that's going across basically the male-female areas, or or I would have like or three partitions and have like the inside be males and the outside be female. It's kind of hard to kind of put it with the way this is being stated, because I have a little bit too many partitions here that would be possible. So I'm just going to use the table to do the partitioning, and I'm going to use the fact that there are 500 registered voters. So, again, these percentages were probably rounded off. So as I do these, I might get some numbers in here that may not make total sense. I mean, at first, the totals, 51% and 49% of the 500 would give me 255 males, 245 females. But then as I look into the other ones, if I'm letting these be number of people or number of men, number of women who answered a certain way, I'm getting decimals, which, some people get alarmed about because they say that doesn't make sense. But in this kind of perspective, it does, because the percentages may have been rounded off, and as a result, I'm trying to make sure that I'm being as accurate as possible when I try to come up with some of these probabilities. But basically, all I did was I took 62% of 255, 32% of 255, and 6% of 255 to get the numbers that I have in the male row. And I did the same thing with the percentages for the female row being multiplied to the 245 to get this table filled in. With this table filled in, I can now answer it more accurately, because sometimes a lot of students, they'll think, well, these percentages are given in the problem here. But I have to be careful about seeing what these percentages are versus what it is I'm asked to do. Because some people would say, like, the answer to part A was this. This is 68%. It was a 68%. Well, that's the probability that somebody is in favor of the lottery given that they are a woman. That is not what we're looking for in Part A. In Part A, we're looking for the probability that a person is a woman given that they favor the national lottery. That's a different circumstance. But with the table, it makes it much easier, because I'm only looking at the first column, those who are in favor. There's 166.6 women, and the total in that column is 158.1 plus that 166.6. And if I carry through that calculation, it's actually more like 0.5131. So about 51.3% of women, 51% of those who are in favor are actually women. So I have to be careful, because I mean the problem that someone being in the group, someone being a woman, given that they are in favor of this lottery, can and oftentimes will be different than somebody who's in favor of the lottery, given that they are a woman. That's what a lot of blurring of statistics happens when you see things, even like especially like all the political things going on this time of year. Some people will state one of these things in place of the other, and people easily get them mixed up and thinking they're the same thing. So just like a number of statements that were made in previous political discussions, there might be data to say, okay, probably of this, given that that's happened, is this, but that was presented as a probability of that, given that this happened. It's not the same thing, but it's presented in the same way, and people often equate it the same way, so you have to kind of be careful of that. And in Part B, kind of the same thing. We're looking for the probability that a person who expressed no opinion was a man. So we're looking for the probability of someone being a man, given that they expressed no opinion. Again, students will look at this table and say, well, that's 6%. Well, no, that's the probability that someone expressed no opinion, given that they were a male. I'm looking for the probability that someone's a male, given that they expressed no opinion. Different. And as I said before, and I mentioned before, sometimes the wording of a question can certainly have a great outcome on how it's interpreted and how it's calculated, or a misinterpretation of thinking it's one thing when it was stated to be another can certainly cause the same kind of thing. So you have to be kind of careful with this. So I'd only be looking at the data from the no opinion column in my table. There are 15.3 males in that group out of whatever 15.3 plus 9.8 would be. total in that group of no opinion people. And so I would have 0.6096 be that probability as compared to the 6% that I had if I stated the probability of someone having no opinion given that they were a male. Vastly different percentages, so with an A, 68%, 51%. Some people say, well, that's at least somewhat close, but 61% versus 6%, that's a huge difference. I mean, so there's no way that those could possibly even be considered the same thing or even, approaching one another. So for the last one, Janssen Electronics has 4 machines that produce identical components for use in its DVD players. The proportion of the components produced by each machine and the probability of a component produced by that machine being defective are shown in the table below. What is the probability that a component selected at random, and they ask you 3 questions. What's the probability that you have just a randomly selected component, from this entire lot being defective? What's the probability of it being produced by machine 1 given that it was defective? And C, what's the probability that it's produced by machine 2 given that it was a defective component? So again, be careful with the way it's wording. We're given that it's defective for B and C. We want to see what probably came from machine 1. Whereas this table would much more immediately give you information about the probability of it being defective given that it came from machine 1, given that it came from machine 2, so forth and so on. So take a moment, use this data, reorganize the data if you need to, or maybe use Bayes' theorem's formula to calculate these things, and then we'll go over it. Okay, again, so now as we go through this, I mean, again, students make mistakes. They thinking that this table may just give them some of the answers off right, and every once in a while you might get a rare circumstance where you might get some information on a table that just directly translates into an answer, but oftentimes you're going to have to work with it a little bit. Because one of the things that we're looking for here, we're looking for the overall probability of being defective. We're also looking for the overall, looking for the probability that it's from machine 1 if it's defective and from machine 2 if it's defective. And some people think that some of these probabilities, are directly going to help us, but not really, because first of all, each one of these probabilities is the probability of me having a defect given that it comes from a certain machine, not the other way around, which is like what B and C is asking. Also, a lot of times people think that if you just add these probabilities together, that it's going to give me the probability of me being defective. The thing is, since these are probabilities given that I'm from a certain machine, these just adding together are not going to do it because, it's 4% out of the 15% that came from machine 1. That I'm looking at here. So again, it's hard to have a direct translation over from percentages, which is what these basically are. These are probabilities, but they're percentages, going right from percentages in a table to percentages that you can make use of for direct calculation. So now, I mean, if I look at these probabilities here, I mean, these do add up to 1, which means each one of these could be representing a percentage. But at the same token, I'm not given a whole number here, so I'm going to use these percentages as numbers. I'm going to use 15, 30, 35, and 20 as, the number of numbers of components. And so the numbers I'm going to come up with when I make my Venn diagram are going to have decimals involved, but, it's going to be based off of these percentages as well. Because when I construct my Venn diagram, I'm going to show my 4 partitions, and anything that's in that oval is in group D for the defects. So if I look at this, if I do 4% of 15%, I do get 0.6. If I do 2% of 30, I do get 0.6. If I do 2% of 35, I get 0.7. And again, if I do 3% of 20, I get 0.6. And those would be the number that are defective from each one of these machines, which means I would have 14.4 that are not defective for machine 1, 29.4 for machine 2, etc., etc. So now I have numbers out of 100 that I can make use of. So now, if I want to add up anything that's in this group up here to get my percentage, then I'll have it pretty easily, because basically I'm going to have 0.6 plus 0.6 plus 0.7 plus 0.6 out of 100. That's going to give me 0.025, or about 2.5%. And now when I want to find the probabilities that it came from a certain machine, given that it was defective, I now have the numbers organized in that Venn diagram to help me along with that. So when I look at the probability that a component was produced by machine 1, given that it was defective, that's going to be 0.6, because that's how many that are defective, out of the from machine 1 that are defective, and there's 2.5, the total of all the defects together. So it's about 0.24, or about 24%. And as you can see, since I have the same number in the defective group for machine 2, it's no surprise that when I do the probability that it came from machine 2, given that it was defective, I get the same value of 0.24, or about 24%. Now again, you could use Bayes' theorem's formula to do this, but that's a lot of writing. I would say if you have enough information to reconstruct that Venn diagram, it makes it a lot easier. You just have to be careful about what you're computing and what you're putting into it, because chances are a lot of times not all the information from the table is going to directly go into there, especially when they're giving you probabilities based off of it being from a group that another probability had been used. But that's all I have for now. If you have any further questions, please make sure to bring them up in class. Until next time, have a good day.